Thank you very much for inviting me to speak. This paper is part of a larger project on the reception of Newton in 18th century Germany, or Germany from really 1687 until the early 19th century. And I'd be very grateful for any sort of comments and suggestions you have, because I'm still trying to understand some parts of this. So the paper is about Christian Wolff and Newton. Now, the philosophy of Christian Wolff and the theories of Isaac Newton are often perceived as very clearly distinct systems, even incompatible systems. Wolff is generally considered a follower of Leibniz, of Gottfried Wilhelm Leibniz, whose dispute with Newton over the invention of the differential calculus culminated in Leibniz's condemnation by the Royal Society for plagiarism at Newton's instigation. Wolff also supported Leibniz in his controversy with the Newtonian philosopher Samuel Clarke. And in many ways, Wolff's and Newton's basic philosophical principles differed significantly. Now, Christian Wolff's relationship to Newton's ideas was, however, more complex than the sort of common opposition between Wolffian or Leibnizian Wolffian and Newtonian philosophy may suggest. Wolff regarded himself as an eclectic philosopher who adhered to no particular school or sect, as he and others put it, but who selected the best opinions among all that were available. He was very critical of Newtonianism as a philosophical school that assumed Newton's exclusive intellectual authority on all matters. But on the other hand, he praised and agreed with Newton on many particular questions and referred to him regularly throughout his works. On the other hand, Wolff's intellectual dependence on Leibniz also must not be exaggerated, and that has been pointed out before. And other figures who are less famous than Leibniz, such as the Altdorf natural philosopher and mathematician Johann Christoph Sturm, or the philosopher Ehrenfried Walter von Tschirnhaus, were of very great importance to the formation of Wolff's ideas, and probably more influential at the time when Wolff was at university than Leibniz was. So what I'd like to do here is to look at Wolff's critical engagement with some central Newtonian theories and their more general philosophical foundations. And before turning to these questions, I think it may be helpful to provide a short summary of Wolff's career, because he's not not very well known in sort of Anglophone scholarship. Now, Wolff was one of the most famous and prolific German philosophers in the first half of the 18th century. He was born in Breslau, which was in the Protestant part of Habsburg Silesia in 1679, the son of a Lutheran tanner who had been educated at a gymnasium, but had not been able to continue his studies by going to university. Now, Breslau was a multi-confessional, biconfessional city. It was overwhelmingly Lutheran, but governed by the Catholic Habsburgs. And in Breslau, Wolff attended the Magdalenen Gymnasium before entering the University of Jena in Lutheran Saxony in 1699. There he was enrolled as a theology student, but he devoted much of his time at Jena to natural philosophy and mathematics. In his later autobiography, he explained that his original motive for studying mathematics especially was his hope that theological controversies might be resolved by the use of mathematical models of argument. And he often comments on the fact that during his childhood he experiences sort of confessional disagreements in his hometown, and that he hoped mathematics would provide some kind of method for reaching agreement. And that he is, I think, quite typical of many 17th century thinkers who try and apply a sort of mos geometricus as a sort of model of argument. Now, at that time, it seems that Wolff was not familiar with Newton's ideas, although the Principia had appeared some years before in 1687. More important to Wolff at this stage were the works of the Altdorf mathematician and natural philosopher Johann Christoph Sturm, a self-declared philosophical eclectic who had written a defense of Robert Boyle's Tractatus de Ipsa Natura, as well as the above-mentioned Ehrenfried Walter von Tschirnhaus, who published a work on logic, the Medicina Mentis, in 1686. In 1702, Wolff travelled to Leipzig to take the examination for his magister degree at the university there. He returned to Jena to prepare a further disputation which would qualify him for university teaching posts. And this was the Philosophia Practica Universalis Mathematica Methodo Conscripta. In later editions, he changes the title to Methodo Scientifica Conscripta, but he means the same thing. Wolf defended this at Leipzig in January 1703. Now, this disputation was read by the professor of moral philosophy at Leipzig, Otto Menke, who was also editor of the Leipzig Acta Eruditorum, which was easily the most influential review journal published in the German territories. Menke was very keen to recruit Wolf as a contributor and sent the disputation to Leibniz for his opinion. Leibniz responded by writing to Wolf, congratulating him on his work, and thereby inaugurating their correspondence, which continued until Leibniz's death in 1716. So Wolf had already acquired a very considerable reputation by the time he became an academic teacher in 1703. He was very soon offered a position teaching mathematics at the University of Leipzig, where he remained until 1706. He then accepted a post at the University of Gießen, but he turned it down again almost immediately because en route he was poached by the more prestigious University of Halle, which appointed him to a professorship in mathematics. Now, it seems that Wolf had begun studying Newton's works in the early years of his academic career, because in 1705 and 1706 there are anonymous reviews by Wolf in the Acta Eruditorum of Newton's Optics of 1704, as well as references to Newton's Principia, and one of Wolf's early works is Aerometriae Elementa of 1709, which was a discussion of various experiments involving air pressure. And from 1710 then, there are numerous references to Wolf, to Newton to be found in Wolf's works, which covered really the full spectrum of philosophy, all the sort of areas of philosophy in the early 18th century. Also in 1717, the Leibniz-Clark correspondence first appeared, and Wolf wrote a preface for the German edition, which was published in 1720, and which included a reply by Wolf's pupil Ludwig Tümmich to Clark's final letter, to which Leibniz had not been able to respond before his death. Now, in his preface to this edition, Wolf took the side of Leibniz, arguing that Clark had overrated sense perception as the source of philosophical truth. Sense perception, he said, could not be the foundation of certain knowledge, which had to be grounded in, quote, allgemeine Begriffe, that is, universal rational truths. Wolf also sided with Leibniz on a particularly controversial issue raised in the debate with Clark, the freedom of the will. In his vernünftige Gedanken von Gott, der Welt und der Seele des Menschen of 1720, Wolf cautiously endorsed Leibniz's pre-established harmony as the best means of explaining the relationship between mind and body. And this meant that Wolf, like Leibniz, argued that the human will was not free in the sense of being indifferent, but because it was spontaneous, that is, not determined by anything external to the human soul, although it was always a product of its own internal principles of development. There always had to be a sufficient reason for a particular volition. It was impossible for the human will to be in a state of true indifference to the various physically possible courses of action and yet arrive at a decision. In that respect, the actions of the human will were necessary, but because they were not subject to the mechanical necessity of the physical world, Wolf argued, they were also free. Now, Wolf's views, however, exposed him to criticism from leading Pietist theologians at the University of Halle, especially Johann Joachim Lange, who wrote that, quote, the liberty of free agents must not be confused with spontaneity, which pertains even to brutes and to automata, and to causes acting from natural necessity. Now, Wolf's apparent defense of fatalism caused him to be expelled from Halle and the territories of the Elector of Brandenburg in 1723. He found refuge at the University of Marburg, where he became professor of philosophy and where he taught until 1740, when Frederick II of Prussia, who had just succeeded his father to the throne, managed to persuade him to return to Halle, where Wolf stayed until his death in 1754. Now, Wolf had a very high opinion of Newton as a mathematician, describing him as an, quote, outstanding geometer who enriched mathematics with so many famous discoveries and advanced the mathematical understanding of nature to such a degree that he deservedly enjoys the greatest esteem wherever the mathematical sciences are held in high regard. Now, his praise for Newton's mathematical achievements was, however, qualified in very significant respects. Newton, he said, had followed the examples of Archimedes and Galileo in applying geometry to the interpretation of natural phenomena, and he had been remarkably successful in doing so. but he had exaggerated the importance of mathematics for natural philosophy. Now, mathematics was useful in measuring and quantifying natural phenomena, but it fell short of offering true causal explanations for them. For example, the fact that an arithmetic formula could be used to calculate the speed of a falling object did not mean that the object fell because of this particular mathematical relationship. Mathematical laws of nature, Wolff said, were fictions. They were adequate to describing the regular course of natural events, but they were not, quote, the true causes by which the effects of nature are explained in an intelligible fashion. Now, Newton seemed to have admitted as much himself in Book 1 of his Principia. There he suggested that the purpose of the mathematical propositions he set out was not to find the causes of the phenomena they were concerned with. Indeed, it was essential to his method not to try to do so. Propositions in physics were based on phenomena and, quote, whatever is not deduced from the phenomena must be called a hypothesis, and hypotheses, whether metaphysical or physical, or based on occult qualities or mechanical, have no place in experimental philosophy. In this experimental philosophy, propositions are deduced from the phenomena and made general by induction. Now, this meant, in the case of gravity, for example, that it was enough to know that it, quote, really exists and acts according to the laws that we have set forth, as Newton put it. There was no need to know its physical cause, which for the time being had to remain a matter for speculation. Now, Wolff argued, however, that it was impossible to deduce propositions in natural philosophy a posteriori by purely empirical methods, as Newton had demanded. Abstractions from sense perception were, as Wolff put it, only, quote, imaginary rather than, quote, real notions. Now, by calling them imaginary notions, he did not mean they were invented, but that they were based exclusively on sensory experience, which was processed by the imagination, the human faculty responsible for receiving images, that is, representations of the external world, via the sense organs. And these sense images, however, were a very poor guide to the truth. They only offered, as Wolff put it, obscure notions, and they represented external reality, quote, in a confused fashion. Wolff criticized John Locke especially for believing that sense perception by itself could lead to simple, distinct ideas on which then more general propositions could be grounded. Newton's natural philosophy was another example of this excessive confidence in the evidence of the senses. Sensory experience had to be subjected to some kind of critical evaluation, the principles of which had to be independent of sensory experience itself. Now, Wolff concluded that empirical observation had to be combined with metaphysical a priori reasoning that was derived from the intellect alone. And it was only through such metaphysical argument that the transition from the obscure, quote, imaginary notions based on sense perception to real and distinct notions could be made. Now, according to Wolff, there were two main relevant metaphysical principles. The first was that of non-contradiction, according to which a hypothesis must not be, quote, impossible in itself. That is, it must not involve, quote, a contradiction when it is considered by itself. Now, that was adequate to judge the truth of mathematical propositions, but not that of propositions in philosophy, including natural philosophy, which were concerned with the causal explanation of events in the real world, not just with internal logical consistency. Now, philosophical propositions had to meet the requirements of the second metaphysical principle, that of sufficient reason, which stated that there was nothing that did not have a sufficient reason for its existence, because it was logically impossible for anything in creation to exist without having been caused by something else. For if that were the case, if things could exist without having been caused by something else, the absurd conclusion would be that something could come into being for no reason at all, and thus at any time and entirely at random. Now, Wolff believed, that Newton's explanations of natural phenomena failed to identify sufficient reasons for them. And the reason, Wolff believed, was that Newton restricted himself to a narrowly mathematical interpretation of natural bodies in terms of their external measurable and quantifiable properties, their physical extension in particular. And this, Wolff said, was typical of mathematicians. Descartes, for example, he said, had done the same. Yet it was not clear then why the physical extension of a body should, for example, cause it to drop to the ground, or in the case of an iron object, to be attracted by a magnet. Now, these puzzles, according to Wolff, compelled Newton to introduce the idea of forces of attraction between material bodies. And the problem with this solution, according to Wolff and many other critics at the time, was that it represented, in effect, a return to a scholastic notion of occult powers, despite Newton's claim to have dispensed with them. Now, Newton's theory of attraction, Wolff argued, was a version of the discredited belief in action at a distance. It appeared to attribute to material bodies some kind of agency, an ability to influence other bodies without any direct physical contact with them. According to Wolff, however, it was not clear how this could be true. Wolff's understanding of nature was very strictly mechanistic, and that he believed any influence of one material body on another had to depend on physical contact between them. So unless they sort of collided or there was some physical contact between material bodies, then nothing could happen. When action at a distance was impossible, quote, one body does not act on another unless it impinges upon it. All changes in the states of material bodies only came about when they collided and their motion or shape changed as a result. Now, Wolff believed that if Newton had applied the principle of sufficient reason, he would have realized the weakness of his ideas of action at a distance. Now, of course, Wolff did not deny that a piece of iron moved towards a magnet when it was brought close to it, even if the two did not touch. His point was that this movement of the iron towards the magnet could not be due to some power of attraction in the magnet. There had to be another third corporeal substance, even if it could not be observed directly, that acted on the iron through physical contact and caused its movement towards the magnet. The same principle applied to other natural phenomena, such as gravitation, which Wolff also tried to explain with the immediate action of one material body on another, rather than with forces of attraction between physically separated bodies. In 1710, for example, he published a piece in the Leipzig Acta Eruditorum in response to the Newtonian John Kyle, who had defended himself against early criticisms by Wolff in the Aerometriae Elementa of 1709. Now, the dispute between the two philosophers was mainly about the possibility of a vacuum in nature, but it also involved a discussion of gravity. Now, Kyle argued for the existence of a vacuum, saying that if there were two bodies of equal size but unequal weight, this meant that the lighter of the two had to contain less matter than the heavier. And this implied that the lighter body had pores that were, he said, absoluta vacua. If these pores were filled with matter, then the quantity of matter in both bodies and thus their weight would be equal. Wolff replied that the difference in weight indicated the existence of two different kinds of matter, which he, in this piece anyway, called materia coherens and materia interlabens. The latter was a corporeal substance that filled the pores between pieces of the former. It had no weight of its own, but it caused the heaviness of the bodies with which it came into contact. So gravitation was a form of local motion, and the cause of the motion could not be in the moving body itself, because that would be an explanation in terms of occult qualities. It was evident that there had to be a separate external cause of gravity that could not itself be heavy, because it would then require another external cause of its own heaviness. Now, given Wolff's mechanistic interpretation of nature, this cause had to be material, and it had to act through direct physical contact. So Wolff did not deny the existence of forces in nature, but unlike Newton, he assumed that these forces between bodies operated only through direct contact, or you believed that you hadn't really come up with a proper explanation unless you had, unless you provide an explanation based on this idea of bodies acting through direct contact. Now, Wolff also argued that it was impossible to understand these forces purely on the basis of empirical observation. And it was in trying to do so that Newton had been forced to invent forces of attraction at a distance, because the external measurable and quantifiable properties of material bodies were not sufficient to explain phenomena such as gravitation. Proper proof of particular forces in nature demanded a connubium, as a marriage of metaphysical a priori and empirical a posteriori argument. And the force of inertia was an example. Now, Wolff agreed with Newton on the existence of inertia in material bodies, and repeated Newton's first law of motion from the Principia, which stated that, quote, every body perseveres in its state of being at rest or of moving uniformly straight forward, except in so far as it is compelled to change its state by forces impressed. Wolff felt, however, that Newton had not demonstrated the necessity of this law of inertia, but only stated its existence. Wolff argued that the law of inertia was evident from the metaphysical principle of sufficient reason. Any change in a body's state required a sufficient reason. This reason could not be internal to the body, because it would not be clear then why this reason had not caused the movement before. The reason why a body at rest began to move, therefore, had to be external. Changes in the speed and direction of movement also had to have extrinsic causes, just as a moving body returned to a state of rest only under the influence of an external cause. Such changes could only be brought about through the action of another material body, but it could not be the action of any other body that produced the change. If that were the case, it would not matter which other bodies came into contact with the first body in which the change was effected, and as Wolf put it, quote, there will no longer be a reason why some particular force moves a body rather than not moving a body, rather not moving it. Thus, every material body resisted a change in motion to some extent, and if it did not, the notion of a sufficient reason in explaining the outcome of collisions between bodies would be meaningless. Now, Wolf also drew on the principle of sufficient reason to explain Newton's third law of motion, that, quote, to any action there is always an opposite and equal reaction. In other words, the actions of two bodies upon each other are always equal and always opposite in direction. As Wolf argued, if one material body acted on another, there had to be a sufficient reason for its action. This reason was that the inertia of the body that was acted upon had to be overcome before there could be any change in its motion. If the body acted upon did not resist change, there was no need to act on it. The force of the action was necessarily equal to the force of the resistance that had to be overcome for change to take place. Hence, the action of one body was equivalent to the reaction of the body it acted upon. Now, Newton's laws of nature, Wolf believed, failed to explain natural phenomena in terms of the metaphysical principle of sufficient reason, and thus nature ended up appearing as a succession of regular but uncaused and hence accidental, in that sense, accidental events. In effect, Wolf believed that Newton's narrow conception of corporeal substances in terms of spatial extension and his refusal to consider the metaphysical dimension of natural philosophy reduced the course of nature to chance. Newton's theories, Wolf said, were thus only a more sophisticated version of the notorious views of the ancient Epicurean atomist philosopher Lucretius, which were widely rejected by 18th century philosophers. Now, Wolf also argued that Newtonians applied this interpretation of material bodies to the elementary parts of nature, believing them to be tiny extended pieces of matter, atoms no different in principle from larger bodies and only distinguished by their size. Yet Wolf wrote, quote, when one thinks a little about it, one finds very quickly that the elements of things cannot be discovered by observing composite bodies, nor do they have the same properties. Wolf believed that the elementary particles of nature did not have the same properties as the material bodies they composed. These elements were not extended in space, they had no shape or internal movement. They were thus different in kind and had to be if they were meant to explain the properties of extended bodies. Unlike extended bodies, they could only cease to exist by being annihilated, while extended bodies could be dissolved into their component parts. Newton, on the other hand, thought of the elementary particles of material bodies as tiny material atoms which were extended in space but indivisible. Now, the corpuscles, according to Newton, adhered to each other through forces of attraction which were extremely powerful due to the very short distances between these particles, but which diminished as distance increased. Wolf considered this just another example of the sort of atomism that was characteristic of ancient thinkers such as Democritus and Leucippus, and of moderns such as Walter Charlton. Now, Wolf's notion of elements also marks an important difference between his views and those of Leibniz, whose theory of monads he did not exactly follow, because Wolf's elements were physical, not metaphysical entities, and unlike Leibniz's monads, interacted with each other. Now, aside from inertia, Wolf identified several other physical forces in nature. Like Leibniz in his Specimen Dynamicum of 1695, he distinguished between primitive force, vis primitiva, and derivative force, vis derivativa. Leibniz had defined the former as that, quote, which is inherent in all corporeal substances as such. Although this was necessary to explaining motion and the interaction between material bodies, it was not sufficient for doing so. Doing so required the notion of derivative force, which bodies acquired as a result of collisions with each other. Another important distinction was that between active and passive force. Active force, vis activa, was that exercised by corporeal substances in motion. Passive force was that which allowed a body to resist the motion of another body and was identical to inertia. All changes of corporeal substances, Wolf wrote, can be explained in terms of their extension, their inertia, and their active force. Material bodies could not modify themselves, for that would mean attributing to them the unintelligible occult qualities favored by the scholastics. Like Leibniz, Wolf also distinguished between dead force, vis mortua, and living force, vis viva. The first was a tendency towards movement without actual motion. A heavy body, for example, that is prevented from falling to the ground because it is suspended from a string. And if the body is released and drops, this dead force acquiring momentum is converted into living force. Now, the notion of vis viva was the subject of a series of controversies between Newtonians and followers of Leibniz over the measurement of the force of a moving body. Newtonians arguing that the force of a moving body was equal to mass multiplied by velocity, and according to Leibniz and Wolff, however, force vis viva was equal to mass multiplied by the square of the velocity. Now, this controversy was continued for some time into the 18th century. It was never really resolved by agreement, and is not important to retrace here. But the significance of Leibniz and Wolff's theory of force was that it was used to illustrate that force depended on much more than the externally observable and measurable properties of bodies. And the conception of force thus had to be grounded in metaphysical arguments. Now, while Wolff's account of physical forces seems to have been broadly inspired by Leibniz, a key difference between the two philosophers concerned their views on elasticity. According to Leibniz, all corporeal substances were elastic, and their elasticity was essential to explaining the communication of motion from one body to another in collisions. Because if there were perfectly hard, non-elastic bodies which rebounded from each other following a collision, the implications, Leibniz feared, would be absurd. Because it would mean that the two perfectly hard bodies in the instant immediately after the collision would abruptly come to a complete standstill before reversing their motion in the next instant and flying apart in opposite directions. Now, Leibniz argued, however, that, quote, in nature no change takes place by leaps and bounds. Instead, the two colliding bodies were compressed like two sort of inflated rubber balls, and as they were compressed, their motion decreased gradually in infinitely small steps until they had come to a complete standstill. And then, quote, as the elasticity of the bodies eventually begins to restore them, they rebound from each other in the opposite direction. Now, Wolff, however, does not seem to have been troubled by this idea of leaps and bounds in nature, and distinguished between elastic and non-elastic bodies, which follow different laws in collisions. In collisions between non-elastic bodies, one of which is at rest, the speed and mass of the impacting body had to be sufficient to overcome the inertia of the body at rest. If it was not sufficient, then the moving body instantly came to a complete standstill, Wolff argued. The same happened if two non-elastic bodies with equal mass collided head-on at equal speeds. Following such a collision, Wolff claims, both have lost their motion and are at rest. Now, yet this outcome only occurred in frontal collisions in which the two bodies involved were moving in diametrically opposed directions. Now, these head-on collisions, which Wolff termed occursus, always reduce the sum of the quantities of motion, the quantitas motionis, that is the masses multiplied by the respective velocities in the bodies involved. Now, Wolff distinguished the occursus from incursus, a collision either between two bodies moving in the same direction or two bodies, one of which was at rest. In the case of incursus, the overall quantity of motion was preserved, although it was redistributed between the two bodies as a result of the collision. Now, Wolff's interpretation of collisions between non-elastic bodies thus differed from Newton's, who argued that even non-elastic bodies would rebound from each other when they collided with each other. In collisions between elastic bodies, Wolff said, the elastic force vis elastica was a function of the force with which the elastic bodies were compressed by the collision. The greater the compression, the greater the elastic force generated, which then influenced the outcome of the collision. In a head-on collision, or courses between two elastic bodies of equal size and traveling at the same speed, the elastic force meant that they did not come to a complete standstill, as perfectly hard bodies did, but rebounded from each other at equal speeds. Now, aside from these laws of motion, another important area of natural philosophy in which Wolff commented on Newton's theories was optics. And Wolff defended Newton against the criticisms of the French natural philosopher Edmé Mariotte, who had failed to replicate Newton's famous optical experiments and who had concluded from this that Newton's theory of colors was wrong. Now, like Newton, Mariotte had let a ray of colored light pass through a prism. And according to Newton's theory, it was then not possible to split this ray any further. Whenever it passed through another prism, it remained unchanged. Yet Mariotte claimed that a violet ray, which had been produced by letting light pass through a prism, was then refracted by a second prism and split into a red and blue ray. But as Wolff pointed out in a piece, Notanda circa theoriam colorum Newtonianam, in 1717, the reason why Mariotte's experiment did not produce the same result as Newton's was that he mistakenly believed the colors produced by refraction through the first prism to be prime colors when it was clear that the heterogeneous rays had not been sufficiently separated from each other. Wolf therefore agreed with Newton's theory of colors, but he differed from Newton over the theory of light. Newton tended to think of light in terms of, quote, corpuscles, atoms emitted from a luminous source such as the sun. Wolf, however, conceived of light as an impulse or wave transmitted through intervening stationary matter between, for example, the sun and the earth. And the speed with which the impulse was transmitted was responsible for the color of the light. So, Wolffianism and Newtonianism, therefore, they were not really mutually exclusive interpretations of nature, and there was very significant common ground between them. So, in general, I mean, the reaction to Newton in the first half of the 18th century is not characterized by sort of uniform hostility. I think there's a fairly sort of common interpretation of the reception of Newton in early 18th century Germany, which says that German philosophy is dominated by a Leibnizian Wolffian school, which is hostile, which is opposed to Newtonian ideas, and that changes in the 1740s when the Berlin Academy under Frederick the Great is revived, and Frederick the Great brings in foreign savants like Euler and Maupertuis, who finally bring about a wider acceptance of Newtonian philosophy within German intellectual culture. But the actual sort of story of the reception of Newtonianism is sort of messier, slightly messier than that, and that there's actually very early engagement with Newton's theories and actually very positive responses to Newton's ideas from people like Wolf. But it's a very sort of a process of very selective and critical appropriation rather than sort of wholesale adoption. Now, Wolf evidently accepted the truth of many characteristically Newtonian ideas concerning, for example, the refrangibility of different colored rays of light, or the importance of action and reaction in accounting for the outcome of collisions between material objects. Now, Wolf's incorporation of Newton's ideas, however, was deliberately eclectic. Like many of his contemporaries, such as the historian of philosophy Johann Jakob Brücker, Wolf declared himself an opponent of sectarian philosophy, by which he meant the uncritical belief in the authority of a particular philosopher. Wolf was willing to praise Newton and agreed with him on specific questions, but he opposed, quote, Newtonianism, the attempt, as he put, the attempt, quote, from the mathematical principles of natural philosophy and from the optics of the supreme mathematician Isaac Newton to try to formulate I do not know what sort of Newtonian philosophy. This Newtonianism, Wolf believed, represented philosophical dogmatism and sectarianism, blind adherence to the opinions of one great but fallible individual, Newton, great and fallible individual. Newton himself, Wolf stressed, had never claimed to be introducing such a system. It was his followers, such as Henry Pemberton, who were to blame for the belief that Newton had established the foundations of an entire new and superior philosophy. Newton's strictly mathematical approach to the interpretation of nature, however, Wolf believed, lacked the sort of comprehensive and robust intellectual foundations a system of philosophy needed. And Wolf therefore thought it necessary to supplement Newtonian ideas with metaphysical principles, without which he felt Newton's theories could never offer a sort of properly convincing causal explanation of the phenomena they described. And I'll stop here. Thank you very much.